electrons?
That's correct. Electricity is the flow of electrons through an electrical circuit, or the movement of electrons flowing along a conductor. Now, um, how do we get electricity? So, electricity is generated in power plants, and the power plants deliver it to us, the consumer, via transmission and distribution lines that's known as the grid. Ever heard that phrase, the power grid? What that was in Texas a couple years where the it went down. That's
No,
what.
it's a year.
Yeah, every year. That's what they were referring to. So they are generating the electricity and basically distributing it to us. Now, once it gets to our residential neighborhoods, we have what's called a transformer. I'll show you a picture here in a second, but the transformer is that like silver box that sits up on the pole. It decreases the voltage to make it appropriate for residential. So the power that the plant is generating and delivering via the grid is too powerful for our residential home. So we need that transformer to sort of decrease it to make it appropriate for residential. Electricity essentially travels in a circuit, right? Or excuse me, in a circle. Think about a circuit as like a circle along a hot wire or an energized conductor. When you hear that term conductor, we're just talking typically about a wire, right? So it travels along that circuit, goes to the load or to the piece of equipment that needs the power, and then it returns back via the neutral or grounded conductor. So I want you to draw a circle in your notes and indicate that the electricity is traveling along that circuit. Draw you a little light bulb or the word load, and then draw it so that it goes back via the neutral. That is essentially an electrical circuit. Let's look at it in this way. Think of it like being similar to the water pipes, right? So we just learned about plumbing and how that works. Electricity flows along typically copper wires because they are good conductors, just like how water flows through pipes. Okay, the water needs a force, or the electricity needs a force to keep it moving. That force is called voltage, or the pressure. Voltage is measured in volts, indicated by the letter V. So, again, this is the force that is pushing the electricity through or along the circuit. Without voltage, your electricity would not flow. So, if we are comparing this to a water hose, it is like voltage is like, think of it like water pressure. The more pressure that you have means the more water that gets pushed through the pipe. So in a wire, the voltage is pushing the electrons through your conductor or your wire. Every device is built to handle a certain amount of voltage. This is what we call the voltage rating. So, for example, most everything in our homes in North Carolina, in North America, are rated for 120 volts because our outlets, they supply 120 volts. So that means you plug something in into your outlet, it's getting 120 volts of pressure pushing electricity into it. So if you buy a light bulb and on the box it says 120V, that means that it was built to work with 120 volts of pressure. And when you screw the bulb into the lamp that's plugged into the wall, everything matches, then the bulb gets the exact amount of pressure that it was designed to handle. So it will light up properly and safely. If the voltage is wrong, meaning it's too low, then the light won't work or it'll be dim. If the voltage is too high, then you may start a fire. Okay, so that's why it is important to have the proper voltage rating, which is something that we'll be looking out for in our inspection. So your outlets, your TVs, small appliances, all of that kind of stuff is going to typically require 120 volts. Your larger appliances, your dryers, your ovens, your AC condenser, those typically require 240 volts. During your inspection, you're going to look to verify that the current voltage is being supplied to every device, that your circuit breakers and wiring match the voltage requirement. So the voltage rating on the device has to match the voltage that's coming from the circuit. Otherwise, again, if it's too little, it won't work. Or if it's too much, you'll create a hazard. Okay, so that's voltage. Next, we've got current. Current is the flow of electricity. So it is the actual flow of the electricity through the wires. So we've got, again, the electrons moving along the conductor, sort of like how the water flows through the pipe. Current is measured in amperes or amps. Okay. So voltage pushes and the current flows. If we're thinking about the water hose, we've got the pressure that's pushing the water through the hose, or the voltage, and then the amount of water flowing. Your current is how many gallons per minute are moving through the hose. So of course, in a wire, instead of water, you have your electrons moving. So the stronger the pressure or the voltage, the more electrons can flow, but only if the wire or the pipe can handle it. Okay, so more voltage can push more current. um every wire, just like with our voltage rating, every wire or device or circuit breakers are designed to handle a certain amount of current. Same thing, too much current, we're going to overheat our wires and devices and likely cause fires. This is why we have breakers, right? The breakers shut the current off before too much current flows. Your appliances list how many amps they draw on the data plate. So again, a microwave might use, say, 15 amps. That's how much electrical current it's pulling from the circuit when your microwave is running. So when you turn on the microwave, it pulls 15 amps of current through your wire in order to safely operate. So your circuit needs to be built to handle at least that amount safely. Same thing with your dryer. The dryer is obviously going to be more, so it may use 25 amps. Your breaker, the wiring outlet, all of that has to be sized to handle that current. Um, just know that there are two types of current. You've got direct current, DC, that only flows in one direction. This is like batteries. And then we've got alternating current, or AC. This flows back and forth. This is what homes use. Okay, I'm not going to get into that. It's sort of like electrical theory, but in our homes, we use AC, or alternating current. So again, current is how much electricity is moving. Too much, we got heat, we got danger. And then last is resistance. Resistance is anything that slows down or opposes the flow of electricity in a circuit. The higher the resistance, the harder it is for electricity to flow. It is measured in ohms. So again, if we are thinking about the water flowing through a pipe, resistance is like how this example here shows, is like having dirt or rocks in a section inside the pipe, and that will slow down the water. So the more obstacles or restrictions inside the pipe, the harder it is for the water to flow. So in an electrical wire, as resistance makes it harder for electrons to move through the conductor. Resistance is affected by the material of the conductor. As I mentioned, copper has low resistance, so it is a good conductor. Aluminum has higher resistance than copper. So that is why back in the day, we used to primarily only use aluminum until we realized that. And then now we use mainly copper. Um, Rubber, plastic, wood, all very high resistance. Okay, longer the length of a conductor or a wire, the longer the wire is, the more resistance. The further the electricity has to travel, the more it slows down. Temperature. As wires get hotter, the resistance increases. This is why overheating makes your situation um worse. Um so in the house where you see sort of this example of resistance in our heating elements, so in our electric stoves, your dryers, our water heaters, toasters, all of these use resistance in order to create heat. So in these devices, resistance is actually what we want because the opposition creates heat. Think about like when you rub the friction, excuse me, generates a heat energy. And so that's what we want in that case. So all of those factors play into having resistance and how we use resistance in order to generate electricity. Okay. So these three factors are like the foundation of the electrical system. Okay. Um, let's see. All right. And Ohm's law is what describes the relationship between these three factors, between voltage, current, and resistance. So again, voltage is what? What is voltage? What does voltage represent?
Pressure.
The force, yeah. Correct. The electrical force that's driving the flow of our current. So it is the push that makes our electrons move. What does current represent?
The flow. The flow. The electron.
Correct. So it is the actual movements of the electrons through the conductor. And then resistance, again, is the opposition to the flow of current. So according to Ohm's law, current is represented here by this I. So current equals voltage divided by resistance. So essentially what this is telling us is again, voltage pushes the electricity, resistance slows it down, current is what actually moves it. Okay? So if we increase our voltage but the resistance stays the same, then we would have more current flowing. Can you picture it? Voltage stays the same. Voltage increases. So more pressure, more push, but resistance stays the same. That would equal more current. If resistance increases, but voltage stays the same, then we would have less current flowing. If you lower voltage or increase the resistance too much, you may not have any current at all flowing. Okay, so let's think about a dryer. A dryer that's rated for 240 for 240 volts is drawing a certain amount of amps or current based on how much resistance is in its heating element. So if the voltage drops or the wiring has too much resistance, the dryer would not heat properly. In another example, if we have wiring, right? If the size of the wire, if it's too small or too much resistance, even if you have normal voltage, it can overheat because why?
The wire probably heat up really fast because it's thinner or smaller.
Okay, why? Which one of these factors
It
would be?
wouldn't be able to handle the amount of voltage going through the wire.
Which one of these factors would influence that?
Not enough resistance. The resistance of the wire.
Well, too much resistance, because if the wire is too small and you have normal voltage, it can overheat because remember, the resistance is going to convert that energy into heat. So that's why wire size and breaker sizing are so important. Okay. Ohm's law just is showing, all you need to know is that it is showing how voltage, current, and resistant are always connected. If you change one, it affects the others. Now, practically, when we out in the field, you won't need to know this. You'll never speak of it again. For testing purposes, again, it's the Ohm's law shows how these three are connected, and tinkering with one of them could change the other. Okay, we got voltage, current, and resistance.
Will you go over that? So you said if the voltage um has the push and the resistance stays the same, there's more current, correct?
If the for the when we were talking about the dryer or what?
No, I think it was just in general when you were talking about the. I
It,
think you were saying something about like if the voltage
if you
if there's like go ahead.
if voltage increases
Mhm.
and resistance stays the same, how does that affect the current?
It's more.
Correct.
Mhm.
If resistance increases but voltage stays the same, how does that affect the current?
Just like how you described the dryer, it decreases.
Less current will flow. So just think about it. Voltage is pushing, resistance is working against it. Edith, you on mute.
Oh, I was just trying to picture it talking in my mind. Like you said, voltage stays the same. Resistance, no, resistance uh, stays the same and voltage is higher. Resistance won't allow it to get to allow more pressure into it, right?
If we increase the push and the resistance stays the same, then we would have more current because we've increased the push. If our resistance increases, we have more resistance and the push remains the same, we would have less current. Think about it like this. Again, because remember, resistance is trying to stop our pressure or our push. So if we increase the resistance and we have the same amount of pressure, then we would have less current. If we increase the pressure and we leave our resistance the same, we would have more current flowing. Make sense? Again,
Yes.
don't get caught up on Ohm's law. The questions as it relates to Ohm's law are just again about these three factors being connected. You don't have to get into like the science or the technical side of it. And when we get out there to inspect, again, we're never going to talk about this again. So don't let that part of it trip you up. Okay. All right. So let's talk about um how we get electricity into our house. So electricity in most of our residential electrical systems are going to be a 120 240 volt single phase system. This means that the electrical system is designed to provide or to give us two different voltage levels. Why do we need two different voltage levels?
Different
Our
appliances.
larger appliances will need more volts.
That's correct. The larger appliances need more pressure or more push. So the system is supplying 120 volts for our lights and our regular outlets, and it's also supplying 240 volts for our larger appliances. So again, the 120 supply is the standard voltage for most of your household outlets, your lighting circuits, so your lamps, your TVs, your computers, your blenders, small kitchen appliances, your 120 volt is going to supply that. Your 240 volt is going to be for your dryer. You have an electric heating dryer, your air conditioner. If you have an electric water heater, those are going to rely on the 240 volt. So to recap, voltage represents what?
Pressure.
The push.
It is measured in,
Volts,
that's correct. Current represents what?
the flow.
Is measured in,
Amps.
when we talk about conductors, what are we talking about?
Just the wires.
Just the wires that carry the electricity. Okay? We have what is called does anybody know what a neutral is? Remember when I said draw the circle? If your hot conductor is carrying electricity to your load, what is the neutral doing?
Ground.
What's the neutral doing? So y'all didn't draw that diagram clearly. In a circuit, the hot, go ahead.
I was just making an educational guess. I was gonna say, is it storing some of the electricity in the neutral?
No, because electricity is constantly flowing. It's constantly flowing. So again, draw the diagram, ladies and gentlemen. A circle, you start off with your power source. It travels along a hot conductor or a hot wire to a load. A load just means a device or something that requires power. So you could represent it with like a light bulb or something. After it powers that load, what happens to it? It doesn't just die. It returns back via the neutral. It returns back to the source via the neutral. So your hot or your ungrounded conductor or wire carries electricity to your devices. The neutral or the grounded conductor gives you a return path for your current because it's always flowing. You understand?
I understand when you say the 3 lines, but this is not 3 lines, and this is why I get confused. See, you tell me this is what I did. I do 3 lines, and it said from the source to the load, from the load to the neutral, and back to the source. But then I look at this, and I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and I get thrown off.
Wait, what do you mean? 1, 2, 3, 4, 5. Where are you saying that at?
I'm counting like then there's the ground and the electrode and the gas or other pipe bonding.
No. So I haven't got here yet. I just want to make sure you understand that in a circuit, we've got the hot wires that are carrying the power or the electricity to the load, and we have a neutral that is returning current back to the source.
Is the red one hot on the screen?
I don't want you to worry about the screen yet. I just want you to understand simply in a circuit, the hot wire is carrying the electricity to the load. The neutral is returning it. I'm getting to bust all this down for you. I want you to write that diagram in your notes. Hot to the load, neutral back to the source. The minimum electrical service for a modern single family home. Does anybody know what it is?
240.
100 amps. 100 amps. The minimum electrical service current. Current is measured in what?
You thinking volts,
Right. Current is measured in amperes or amps. Write that down. It is a test question. The minimum electrical service current for a single family home is 100 amps. Okay, now let's talk about this path of electricity into our house. So, to Augie's point, we have a cable assembly that enters our homes. It is made up of two hot conductors, each carrying how many volts?
120.
That's correct. Each hot conductor is carrying 120 volts. As a part of that cable assembly, we've got the two hot conductors and a neutral acting as our what?
Basically, returner.
Yes, ma'am. Our return.
Acting as return.
So we're going to take this step by step, the path of electricity. So it doesn't show it in this picture, but just picture a transformer right here. This is what the transformer looks like. It's on the utility pole. That's where we start. So, um, the power starts at our utility transformer, which is mounted on a utility pole, or it can be on the ground in a transformer box. The transformer is going to reduce or step down the high voltage electricity that's coming from the power plant to our residential voltage levels, which would be what?
240.
120, 240. Remember, our service is a 120, 240 volt single phase service. Okay. So we have our service drop conductors, which are our overhead service wires that come from the transformer. These are two hot and one neutral. Each hot is carrying how many volts?
120.
That's correct. Our service drop conductors, because just think the service is dropping in from the transformers. Our service drop conductors run from the overhead transformer. Now, if we have an underground service, it is called a service lateral. So you need to always note whether the service is overhead or whether it's underground. So our service drop conductors connect with our service entrance conductors at what we call the service point. This circle represents a splice. So the service drop conductors is one cable assembly again, 3 wires, 2 hot and 1 neutral. There is a splice, which means we cut those wires and we have a new cable assembly, same 3 wires that connect. At that point of connection, it is called the service point. The splice is the service point. After the splice, the conductors become the service entrance conductors, because those are going to be the conductors that actually enter the home. Draw this. As I'm talking, draw it. Don't write it, draw it. No, really, draw it, because I know some of y'all just disregarded that and gonna write it anyway. I said draw it. Hard-headed. Draw it.
What are they called? The little circles?
The service point.
Service point.
This just represents a splice. So just think about it. We got a wire, we cut the wire, that's a splice, and we connect it with another cable assembly.
It's just like it's branching on from for example, on the main water, the water main, and then there's a service line. I mean, that's the way I'm connecting this.
Yes, yes, yes. It is like that, except we're dealing with wires as opposed to pipes. Yes. Yep. You should have service drop conductors, a splice, and then we have service entrance conductors. The service point is significant because
Is the splice the 3 wires that just separate?
the splice is these 3 circles. That's how they represented it.
Okay, thank you.
The service point is significant because this is where the responsibility of the utility equipment ends and the homeowner responsibility begins. So if you have any issues with your electrical equipment after the service point, it is on you. So ain't no point in you calling the power company. The utility company owns everything up to the service point. After the service point, the homeowner owns and maintains the electrical equipment. After the service point, the wires become what? What are they called?
You said after the service point, they become what? You mean service entrance conductor?
That's correct. After the service point, the wires become service entrance conductors. My cable assembly still consists of what?
2 hot
One
wires.
high and one low.
2 hots and a neutral. My neutral is serving as what?
The return.
That's correct. Okay. So now my service entrance conductors, this is their path to the house. First, they go through what's called a service head, or you may see weatherhead or even gooseneck, which is this situation right here. This is mounted at the top of what we call the service mast, which is this vertical area here. So our service entrance conductors enter the gooseneck and go down the service mast. Before they go into your gooseneck or your service head, we want to see what is called a drip loop. This is where basically the wires just dip before they go into the service head just to keep rainwater off. That's the whole point of the drip loop. So before it goes into the weatherhead, a drip loop or a dip in the conductors to prevent water from getting into our service mast. From there, our service entrance conductors enter the meter base. The meter base holds the electric meter. This is, of course, how the utility company measures how much electricity we're using. So the meter base is either a round or a square or a rectangular box that holds your actual electrical meter. If it's round, it is probably a older home. If and is rated probably for like 60 amps. If it's square, that is typically 100 to 125 amps, and then rectangular is going to be 200 amps plus. So again, if you're inspecting newer homes, you're going to see either square or rectangle. If you see a circle, you know that this system probably does not, the amperage is not adequate. Okay. So from the meter base and the meter, excuse me, the service entrance conductors will enter the home. The first place that we enter is, it basically goes to what we call the service equipment. This is what you know as your electrical panel. The service equipment includes your main breaker, your circuit breakers, any switches that serve as disconnections. We consider all of that to be service equipment. So from our service mass to our meter base with that holds our actual meter, and then into our service equipment. This is what, again, you know to be your panel box. This is where the electricity is going to get distributed throughout the house. From that main panel, you have branch circuits that, again, carry electricity to your outlets, your lights, your appliances. We'll talk about that in a second. What questions? No más preguntas?
That was a better explanation than I understood it. So thank you.
All right. I wanna make sure. Yeah, did y'all draw it? Don't lie. It's Sunday. We're gonna draw it together so I can make sure that you have it. Who can walk me through my drawing?
We'll definitely try.
All right, let's get it.
I'm not gonna lie, I can't remember. So, okay, so you get the electricity from your power plant, okay? I can't remember what's on the pole. I can't remember the name of that.
Transformer.
Transformer. Okay, so it enters a transformer. The transformer basically lowers the force or the voltage, so therefore it could be suitable to get into the house.
Lowers
Okay.
it to what?
To your conductors.
No, you said it lowers it so that it's appropriate for a residential house. So what does it need to lower it to?
Oh, so 240 and 120.
120, 240. Okay.
Yeah, 120, 240. Your 120 is for your smaller appliances, light bulbs, and then the 240 is for your larger washer, dryer, all that good stuff.
Okay.
And then you're going to have 3 conductors. These are called your service straps. It's going to be 2 hot wires and then 1 neutral. The neutral, so the neutral basically kind of like recycles the electricity.
Or it serves as a what?
Oh, like a return?
Correct. A return path. Okay. So
Return path.
let me actually do this. I'm gonna write these in red. So we've got 2 hots, and each of them are carrying how many volts?
120 volts.
Yes, ma'am.
And then you have 1 neutral.
It
serves as a return.
Okay.
Sorry, go ahead.
No, you go ahead.
And then you're going to have 3 splices on each wiring, which is also called a service point.
Okay.
Okay.
What's significant about the service point?
Oh, I believe at the service point, the homeowner is responsible for basically what happens after that. So the company, the electrical company, is no longer responsible for
That-
what happens.
That's correct.
And then you're gonna have a drip lag.
Hold
So
up.
it's gonna
Hold
go
up.
ahead.
So after my service point, my service drop conductors continue. Is that what you mean?
Yes, they do continue.
My
so
service
the-
drop conductors?
The service drop conductors. No, they became a service point. Yes, they became a service point.
This right here is the service point. The service point is literally the splice.
Correct. So those are going to continue.
My service drop conductors continue.
Your service point.
The splice is the service point. After the splice, where you said after the service point or the splice, that's where my responsibility as the homeowner takes place. So
Correct.
After the splice, am I still talking about service drop conductors?
They're supposed to come into the mast, right?
What's supposed to come into the mass?
I thought it needed to enter the gooseneck first.
What needs to enter into the gooseneck first?
Service entrance conductors.
Oh, the service entrance.
Service entrance. Remember, after the service point, now we are about to enter the house. We just, from the transformer, we drop the service drop conductors. After the service point, we're talking about service entrance conductors. Okay, so
Yes.
the service entrance conductors, what?
They're going to enter a service head or a gooseneck.
Before that, we need to have what?
A drip loop, because rain needs to be able to basically cascade off of
Okay.
the wiring.
Okay.
That enters a gooseneck.
Mm-hmm.
Then the wires go down a service mast.
Uh-huh.
And it's going to travel down vertically into a meter base.
Uh-huh.
Okay. Your meter base, that's where you're going to see your meter.
Uh-huh.
See the circle. If the circle is for older homes, you can see it square, rectangular. That's actually how the company or the electric, how you get charged.
Okay.
For your electricity. And then it goes through the service raceway, and then the wires continue, then it's going to go to your service equipment, or i.e. breaker. And then you have your branch circuits in the breaker, and then that's how electricity gets into home. What did I miss?
Sound good to me. Did she miss something?
Nah, she was on point.
Does everybody have this drawing in your notes? Labeled properly? Transformer drops are conductors, are service drop conductors. 2 hots, 1 neutral. Each hot carrying 120 volts. This is a 120, 240 volt single phase residential system. My 2 hots and my neutral at my service point or a splice then become service entrance conductors because they're about to enter into the house. They are headed to the gooseneck. Before they enter the gooseneck, the weatherhead, the masthead, whatever they call it, I need to see a drip loop to shed the water. They travel down the service mast, which is basically, just think of it like a tube. Because remember, these are wires. This is a cable assembly. So the service mast just serves as like a tube to protect them. Comes down to the meter base. The meter base contains the meter. From the meter, the cable assembly will enter what you know to be your electrical panel, where the service equipment is held. Service equipment is my main disconnect, my circuit breakers, anything that serves to disconnect. That's my service equipment. So now my two hot conductors are connected here in my electrical panel. And from here, I'm going to have circuit breakers that then carry the electricity out to all of my electrical circuits to serve my wires, my lights, etc., etc. We got it? Any questions on this? You must know this. This is the foundation. You got to know it. No mas. Okay. So let's look at it. This diagram is actually in your book. Okay. So again, in our residential service, we've got our two hot or ungrounded conductors. These are the red. So that when we say single phase, we just means the electricity is coming into the home. It has two energized or hot wires. Okay. Each supplies 120 volts. Together, they provide 240 for our larger appliances. Along with that, we have one neutral or grounded conductor, which completes our circuit and allows the current to return. So you see, transformer. This doesn't show the splice. Our service drop conductors, splice, service point, service entrance conductors, drip loop, gooseneck, mass, meter base, meter into the panel, which is the service equipment, goes to provide the power for the load, and then it comes back. This is continuous. Okay. Now we've got clearance requirements for our service drop. Obviously, right? We don't want, these are carrying electricity into the house and they're dangerous if they are touched. Right? So if someone touches them, they doing something on the roof or something like that, you could be shocked. We are also good conductors. People, we are good conductors. So we can be electrocuted. Okay. So these clearance requirements are designed to prevent any sort of contact, accidental contact, and have safe access. So they're trying to keep the wires high enough above the roof so that if somebody's working on the roof, they won't touch them. So that the wires don't sag. You don't want them to rub on your roof surface either. Okay. So for roof decks where people could walk. Okay. So like flat roofs, balconies, patios, because people walk here, stand here. Again, the wires have to be very high. So the minimum clearance is at least 10 feet above the roof deck. If you have a roof with a slope that's less than 4 and 12, the minimum clearance requirement is 8 feet above the roof surface, at least 8 feet above. If it has a fence or it's guarded, then the clearance can drop to 3 feet. But just know, keep in your mind, for a roof with a slope of less than 4 and 12, the minimum, at least 8 feet of clearance. If the slope is 4 and 12 or greater, so this is a steeper roof, You are going to be less likely to have people walking on this roof. So the clearance requirement is lower. The minimum clearance for a roof with a slope of 4 and 12 and greater is 3 feet above the roof surface. There's an exemption. They call it the 18-inch exemption, which just means that when the wires come in contact to the edge of the roof and they're not running all the way across the roof surface, then you could have the 18-inch exemption. So 2 conditions must be true. The service drop cables they're less than 4 feet. They run across the roof 4 feet or less horizontally, and they rise no more than 6 feet vertically along the roof. If that is the case, then your clearance can be reduced to 18 inches above the roof. So basically, again, that exemption is for when your conductors are not really, they're not covering, or they're not mostly hanging over the roof. If they just slightly are on there, then that's when that exemption can come into place. We also have them to opening. So the clearance is also to protect people from actually being able to reach out and touch. And if you open up your window or your door, if you standing on your balcony, we want you to be protected as well. So clearance is required if you have a operable window. So it needs to be 3 feet horizontally from your wires to the window. Same thing with a door. 3 feet horizontally from the wire to the door. Same thing for any sort of balcony or deck. 3 feet horizontally. If the window is fixed, meaning it doesn't open, or if the wires are inside a jacket or conduit, then there's no clearance. What would this represent?
Your service mast?
That's correct. The service mast. So remember when I said, think of it like a tube, the technical term is conduit. So our cable assembly is inside of this conduit that we call our service mast. So in that case, there is no clearance requirement because you couldn't reach out and touch the wires because they are held inside of the conduit. Okay. So all of this again is about danger for reaching. If someone can open up the door or stand out the window, a kid or something like that, and touch the wire, it's a hazard. Next, are clearance requirements above the ground. So the minimum distance between your service drop and the ground or a walkway is 10 feet. Minimum, at least. Whatever word or phrase makes the most sense to you. Use that in your notes. Why did that disconnect? Hold the line. Can y'all see it now? Okay. So the minimum distance between the service drop and the ground or walkway is 10 feet. Minimum distance between the service drop and your driveway, 12 feet. Minimum distance between the service drop and the street parking lot is 18 feet. So just remember, the further away you get from the house, the larger the number becomes. And again, this is minimum distance. So if a question asks you, if it says something about in a residential driveway, there's a car and the service drop conductors are 14 feet above the driveway. Is that cool? Is it cool?
Yes, because the minimum is 12.
That's correct. Okay, we good on the clearance requirements?
Question on, like, let's say, what about pools? Like, let's say the service runs around on top of the pool.
You shouldn't have service drop conductors over pools at all. That would be a defect all day long, every day of the week, if the conductors are over a pool. Ooh, it's 8:30. All right, we good? All of these diagrams are in your book. So these are the same ones that come directly out of the book. Let's get to your panel. So again, our service equipment is essentially the main disconnect point for all of the power to the house. We call these main disconnect, main breaker, service disconnect. So again, circuit breakers, all of our, if you have fuses, switches, circuit breakers are most common, but these are all considered to be service equipment. Your power must be able to be disconnected with no more than 6 touches of your breakers. Write that down. It's a test question. So basically, you must be able to disconnect your power without having to make more than 6 motions, essentially, or moves. No more than 6 moves to disconnect the power. So like Edith said, our main water shutoff is sort of like our main disconnect in our panel. So these are again the technical terms. I'm going to go back and forth because most of us know this. We refer to this as strictly just the electrical panel, the breaker box, the main panel, something like that. But technically it is called an enclosure. So it's either a metal, usually a metal box that houses the service equipment, typically going to be made of galvanized steel so that it can be rated for wet locations as well. We have a couple different types of enclosures. We have our meter main, which is this one here. The meter main enclosure would include your meter disc, your meter. So you see here, the disconnect, which you can't see it in this picture, and then your panel board all in one enclosure. Your main breaker with panel board has the main breaker, this is it right here, the main way to shut your power off, plus all of your branch circuits here, all in one enclosure. And then your main lug. This has no main breaker inside and is fed from a main disconnect that's somewhere else. These are typically used for sub panels. Okay, so if you have a panel, what they call downstream or after this main, it's a sub panel. In your sub panel, just write this down because it's a test question. I want to make sure you have it. In your sub panel, grounds and neutrals must be separated. I'm going to explain all of that, but just write it down. In a sub panel, grounds and neutrals must be separated. Now, our panel boards, we've got single bus panel boards, which is what you will mainly see. This is like what you know to be probably like your regular panel. You've got a bus bar that supplies all of the breaker. In your single bus, everything is controlled by this one main breaker. It's usually at the top. In your split bus panel board, there is no single main breaker. You've got an upper bus, which typically houses your 240 circuits, and then you've got a lower one that's powered by these up here. In most cases, again, you will be seeing single bus. You can have your enclosures, your panel boards in basements, garages, as long as you meet the clearance, which we'll talk about in a second. They may not be in bathrooms, closets, behind appliances. You can't put a picture over it, not behind any decor. Sometimes I've seen it a couple times be in the bathroom. That is a defect. Now we have clearance requirements for our panel as well. We need a working space depth. So that's in front of the panel. There needs to be a minimum of 36 inches or 3 feet. So if we're standing in front of the panel, there should be at least clear space of 3 feet.
I have a quick question.
Uh-huh.
So if you find them in a closet, that's automatic defect? Okay.
A working space width of a minimum of 30 inches. And a headroom space of 78 inches minimum. For your main breaker, it can't be more than 79 inches off the ground. And then the door for your enclosure must be able to swing open at least 90 degrees. So this is basically talking about if you have stuff in and around your panel board, your enclosure, your box, as you guys would call it. So the area that's above and below is only for electrical equipment. You shouldn't have any plumbing pipes, any HVAC pipes. You need to be able to reach this without having to climb or use a ladder, without moving items. That's what we're getting at with these clearance requirements. If you have is blocked or hidden in any way, that is a reportable defect. Okay. All right, now let's talk about some of the components of your panel. First, we have the dead front cover. That is this here with the door and everything. So you see these screws right here? 1, 2, 3, 4. These screws remove the dead front cover. You must remove this to actually view the panel board inside. So this is basically just serving as protection so that you don't accidentally touch any live wires and so that nothing can get to your wiring. The openings in your dead front allow the handles for your breakers to come through. So during an inspection, if safely possible, you want to remove the dead front cover because you need to be able to see the wiring. Our main breaker or your service disconnect. This is the main shut off switch for all of the power in your panel. Again, this is like our main water shut off, how we can use that to kill all of the water to our home. We use this to kill all of the power to our home. Now, keep in mind, this right here, these are our two hots that are coming in. Our service entrance conductors, 120, 120. And this right here is our neutral. We just learned the path. So when we say they come into the box to the service equipment, this is what we mean. They connect right here. So now, before we brought these two conductors in, this panel was not energized. Now it is hot. We are bringing in the power. So even if you turn off this main disconnect, these conductors are still hot, because they're getting their power from the transformer.
Okay, what is that silver wrapped wire on the right.
This right here, this is the neutral. This is stranded aluminum.
Anything is not supposed to be wrapped.
It can be, but it doesn't have to be.
Okay.
This is stranded aluminum. It is our neutral. You will be able to tell because they're going to be the largest conductors in there, whether they're sheathed or covered or not. 2 hots, 120, 120, neutral. Typically, it's at the top of your panel, and it's going to be, this is our service size. So remember, our minimum is 100 amps. So again, our main breaker would disconnect the power to all of our other branch circuits. Our service entrance conductors, these 2 large wires, they're coming from the meter into the panel. They're bringing the power from the utility. Bus bars. Bus bars are our metal bars that basically they're fed directly from that main breaker, and our circuit breakers snap into the bus bars to make contact. And that's how each one gets power, by being physically connected to a bus bar. So this is our main bus bar here. And we also have what we call a neutral bus bar and a grounding bus bar. So they're carrying power sort of like a highway. And then your breakers are like ramps that connect to this highway and send electricity to each circuit. So this one isolated here, our neutral bus bar. So this is what we're seeing right here. Our neutral is connected to the neutral bus bar. Same thing right here. This is our neutral bus bar. This is the bar where all of our neutral wires, which are typically white, will connect. And our neutral does what?
Return.
Correct. Return the current back to the source. In a sub panel, what needs to happen with the neutrals?
It
They
must
need
be
to be
separated.
separated.
In the sub panel, your neutrals and your grounds must be separated. So again, this is our neutral bus bar. This is our grounding bus bar. So this is the bar where all of our ground wires are, either they're bare copper or they're green wires. This is where they would terminate. So in a main panel, you can have neutrals and grounds on the same bus. In a sub panel, you may not. You may not. You may not in a sub panel have neutrals and grounds on the same bus bar. So our neutral wire is carrying current in normal operation. Our ground wire is only carrying current during a fault or when something goes wrong. We're going to talk about here in a minute our grounding system, which is basically the safety system, because again, the electricity is constantly flowing and it's looking for any sort of conductive material to jump onto, and we don't want that. We only want it traveling on the appropriate circuit. But in the case of a fault, we need a safe way or a safe path to clear that fault. That is where our grounding system, our ground wire, ground bus, that's where all of that comes into play. Okay? Our lugs. Lugs are basically these screws. They're the mechanical connectors where our wires attach to the bus bars. So here we have a lug here, here. All of these are lugs, where wire is connected to the bus bars or the terminals. Those are lugs. Basically, they're heavy duty screws and they clamp down on the wires.
Okay, just so I'm following your little circle correctly. Where that red and blue and orange and black, were those connected right above that? You're talking about that's the lug?
The screw
That's
right here, even on the neutral bus bar, each of these screws represents a lug.
okay.
They're like clamps, right?
Ye-
You unscrew it a little bit and then you put it in and you
Yes.
screw it.
Yes. So that's how these wires are secured in here because, like she said, they are screwed down to sort of clamp the wire down. If you unscrew them, then you could remove that wire. All right. A bonding jumper. This copper strap right here is called the bonding jumper. It is basically a metal connection that's inside our main panel that connects the neutral to the ground. So remember, in a main panel, we can have these connected. In a sub panel, you cannot. If you are inspecting a lot of newer homes, you likely will see some sub panels. A sub panel is basically just another ancillary panel to panel a area of the home. It is downstream from the main. So in those panels, neutrals and grounds need to be isolated. In the main panel, they're connected or they can terminate on the same bar, same bus bar. We're going to talk about bonding in a second. But the bonding jumper is just the metal strap. The bonding, we can also use, you see this green screw here? This is also considered a bonding screw. Bonding is just connecting. It'll make sense in a second when we get to bonding, but just know this is your bonding jumper. Green screw is your bonding screw. It's connecting the neutral bar to the panel. So your panel board, when you remove that door, on the door of the panel, it should be labeled. All of your circuits should be labeled. So it should say stove, this, that. All of your circuits should be labeled on the description. So it will list your manufacturer, the model, your max amps, the breaker sizes, all of that kind of information that must be there. That is also a reportable defect if not. So here, this is what I'm talking about. So you could look, excuse me, on this label and see the circuit breakers are numbered. This breaker number 7 serves for the dryer, whatever the case may be. Your breakers should always match the same type, should match the manufacturer of the box. So this copper here is our what?
Bonding.
Mm-mm. See, it is larger over here. This is what it is. This copper piece here. The highway.
Conductor,
Nope.
highway.
Bus bar. Remember, our breakers attach onto here. Let me zoom in so you can see. It won't let me zoom. Oh, there it is. This copper plate right here, this is our bus bar. These breakers clip or attach onto this bus bar. That is how they receive this power from these two hots that are secured here by the lugs. In this picture, we have our two hots and Augie, our neutral is sheathed. Sheathed. Two hots, 120, 120 neutral that is connected to the
Bus bar.
which kind of bus bar?
A neutral bus.
How do you know that?
It's smaller in diameter and I'm assuming the color, the material.
I thought it was connected to its own thingy, that silver thing.
This is the neutral right here. Remember, these are service entrance. The service entrance conductors are going to be the largest conductors in the box. The two hots are going to be connected here to our main bus board, powering all of these breakers. The neutral is going to be connected to its own bus bar. This is the neutral bus bar. On this bus bar, we are going to see typically white wires that represent the neutrals. There is another bus bar that is the grounding. All right, let me back up. Clearly we lost.
It's good, Nita.
Okay. Main bus bar. This is our highway. This is carrying the electrical power, bringing it in. We're going to connect, remember those two hots here, and that's going to bring power. We're going to clip on these breakers to this bus bar. That is how they are going to, these are our branch circuits here. That's how they're able to receive the power. Okay? The bus bars carry the power like a highway. Breakers are the ramps that connect to the highway to send the electricity to each circuit. You have that in your notes? That's our main bus bar. Okay, we also have a neutral bus bar and a grounding bus bar. The neutral bus bar is where all of our neutral wires connect. Neutral wires are typically white. The grounding bus bar is where all of our grounding wires, which are either bare copper or green, that's where they connect. So in this example, this is our neutral. We would have white wires here. This is before any breakers, right? So this is just showing you the bus, and then this is showing you the bus with the breakers and the wires. So main bus, main highway, where our breakers are attached, neutral bus bar, grounding bus bar. This is up close. This is the neutral. On the other side is the grounding bus bar. Neutral.
This is a sub panel, right?
Huh?
This is a sub panel, right?
No. How do we know it's not a sub panel?
Because the neutral can't go into a sub panel.
The main switch, the main
We have a main disconnect.
yeah.
Your main disconnect is only in your main panel. The sub panel does not have the only place you could turn it off is at the main panel.
Okay, that's the main. Okay, no sub panel.
There's no main disconnect. Right.
Main disconnect.
Main shut. Yeah. So in this example, neutral bus bar, grounding bus bar. This is our main bus where we have our circuit breakers attached. They are receiving power from our two hots. So immediately you're going to know what the neutral is because you're going to say, I got my two hots here. I got my neutral. Boom. This is the neutral bus bar. In your main panel, you can have it to where grounds also terminate on this neutral bus bar. So they have it separated, but like you can see over here, there are some white wires over here. So the neutrals and the grounds are together on that one bus bar, a neutral grounding bus bar. That's cool in the main panel. That is not cool in the sub panel. What questions? main bus, neutral bus. The screws are the lugs.
It's my first time really understanding that. You described that great.
Good. Everybody there? If you're not, ask a question.
The sub panels are more like a new version, is that what you said?
A new version?
Yeah, like that's an update.
No. A sub
Or
panel
what are-
is not a new version or an update. It's just another panel. It's downstream from the main panel. Say you have an attic that you want to now bring power to. You can install a sub panel up there to bring power to your attic.
Okay, so are just like making additional more of electric service?
Yes,
Having
yes,
more
yes, yes.
electrical service, okay, got it.
What else?
I got a question.
Uh-huh.
So Nita, the sub panel, it being some that don't have the main shut off, right? When you have the service panel that's on the exterior that does have the main shut off, is that the main panel?
Yes, because remember, you
Gotcha.
can have different. You are having a meter main because you see the meter and the disconnect all in the same box or same enclosure.
Oh, so what Greg is saying is you shut off the main breaker box, it shuts everything off. Because
Yes.
that's the one that's carrying the main from the outside service.
And typically in nicer areas like down in Georgia where Craig is, they sometimes have a meter main. So that means that you're gonna have the meter, your main disconnect, and the panel board is all gonna be in one box, and it can be on the exterior. Maybe you might even see these in Texas too. What we are looking at in our in these examples that we're looking at is the main breaker enclosure type.
Yeah, we get both. That's a good example. So thanks.
What else? Let me see your faces.
It's clear to
No,
me.
it's better.
You cannot
It's-
always see green. Cause none of these pictures, I done seen one green wire, and it's in this picture right here. I ain't seen it nowhere else.
What picture are you looking at?
Oh, right here, right now. Cause one of the things you said in the notes is that our grounding bus bar, we may see green or copper, but that's not necessarily true, right? We may not. Cause this one I see orange.
Where, if you are looking for if we talking about a grounding wire that's green or bare, where should it be?
Your grounding bus bar.
That's correct. These are our branch circuits. So if you're looking for a green or a bare wire, you would only be looking for it on your grounding bus bar.
Oh, okay. So those black things have nothing to do with your lesson today.
But you mean these?
Yeah.
The circuit breakers?
Yeah.
No, I haven't gotten into circuit breakers yet. I just mentioned them to say that they are connected to the bus bar. But in your book, they call them OPDs or overcurrent protection device. We know them to be we call them circuit breakers. I haven't explained those in detail just yet.
So the only place you will see a green or copper is on the grounding bus bar, which in this picture you're showing is on the left-hand side.
I'm not going to say the only place, but if you are looking for grounding wires, your grounding wires will terminate on your grounding bus bar. A grounding wire can be a bare copper wire, or it can be sheathed or insulated with the green sheathing.
Okay. Okay, I got just one more question.
Mhm.
When you go up, you're going up in this panel box on the left.
Mhm.
And then these two sets of silver things at the top with bare copper wires going into them.
So those are the what? Ooh,
What?
you talking about this right here?
Oh, no, yeah.
So what are these? What are they called?
The bus bars, right?
What kind of bus bars?
I don't know. That was my question.
They neutral?
Well, wouldn't that be grounding?
These are the grounding bus bars because Arky, here are
Look at
your
the
bare
color.
here are your bare copper wires. Keep in mind now, inside these enclosures, it don't matter about left and right. These bus bars can be assembled however they could be horizontal. They could be however they want them to be. The way that you know what they are is by what terminates on them.
Okay.
So here we have white wires terminating on this bus bar. So it is a yes, Lord. On this bus bar, we have only bare copper wires terminating on it. So it is a
Brown.
that's correct. On this bus bar right here, if we had white wires and bare copper wires, then what would that be?
A grounding neutral?
Yes. You identify the bus bar by what's terminating on it. It is not on the left or on the right. These panels don't come like this. When you buy the panel, you literally are buying just the box. The electrician assembles all of this bus bars and stuff however they want to, or however they see fit to be able to fit all of the wires and get your branch circuits out. So don't get caught up in left, right, up, down, or none of that.
Okay. Identify the panel by what terminates into
Bus bar, identify bus bar. What else? What else? Clear. Crystal. Clear. Yannicka.
Yes.
Are you clear?
Yeah, I'm just trying to like let it all soak in. But yeah. It makes sense. I just gotta take time to think about it. But it makes sense.
Okay. Let's put this all together. Okay. Why is my thing not I wanted to zoom out now. Okay. So I've got this panel here that holds all of my service equipment. Starting from the outside, I have an overhead service. My transformer, I'm dropping my service in from my transformer. Service drop conductors. My service drop conductors connect with my service entrance conductors at the service point, which is a splice, which is a designation of responsibility. After the service point, the homeowner is responsible for the equipment. My service entrance conductors will enter the gooseneck, the service head. Before doing so, I want to see a drip loop. The service entrance conductors will come down as service mass. When I'm saying service interest conductors, I'm referring to a cable assembly that has 2 hots and a neutral. Each of my hot wires is carrying 120 volts. I have a 120, 240 volt single phase service. From the service mast, I enter the meter base where the meter is held. My cable assembly will continue right here. This is where we see it. This is where we pick it up inside. I got my 2 hots connected here to a lug. 1, 2 connected to the lug. Boom. I've energized this bus bar. Notice this is copper. What do we say about copper? It is very conductive. So now this is energized or hot or power. I've got my neutral that connects here to my neutral bus bar. Throughout my house, I have multiple rooms, multiple outlets, multiple lights, multiple appliances. Each one of my branch circuits is going to serve that. On a circuit, I may have, this is our circle now. When we talk about that circuit, we start at the source, we go to the load, come back to the neutral. I may have 2 outlets on one circuit. My neutral, the return wires, they come back and terminate here. If you were to unscrew, I want you to try this. When we get out of class, unscrew one of your receptacles and look behind it. You will see a white wire connected there. That white wire would be coming back to your panel and it would terminate on your, yes, on your neutral bus bar. Same thing with the ground. Each of our pieces of equipment should have a ground that is connected to, say, the receptacle, and then it terminates back here on the ground bus bar. Does that make sense?
I won't be able to tell that.
You want to be able to tell what?
Like what wires go back to the bus bar.
What do you mean?
I was just making sure that they didn't think they'll be able to like know exactly which wire is going back and where it's going to be, if that makes sense. Or are you able to?
Wait, you say which wires are going back? What do you mean by that?
So you referenced if they were to take a receptacle,
right,
and see that white wire,
right,
and be like, okay, yeah, it's gonna travel back to the neutral,
right.
but to know exactly which one.
Yes, you won't. Yeah. Because it's traveling, so you won't know which one. I just want you all to know that all of these wires that terminate on your neutral bus bar are coming from the different circuits throughout your house. We don't know which ones. That's way beyond our scope. Same thing with the ground. You can see it at that point at the load, and then you see it back in the box. But the wiring, this is, remember when we talk about notching and boring and different things like that, is going through the structure of the home to come back to the box. So no, we will not be able to tell. And that is also why the circuits are labeled, so that you will know. In that case, you can't see it, but you will know, okay, this is my washing machine. It'll be like washing machine. This is my circuit for that. So you'll know that it is powering your washing machine.
That's good. That's so good.
I think your comrades would beg to differ, Craig.
No, it makes sense.
It makes sense. I mean, but sometimes, like I'm thinking about the house where I've routinely gone back to, and when I'm just being walked around, that cabinet, that stuff faded. You can't see the right, like it's peeling off.
That's the defect.
Okay.
The circuits must be clearly and properly labeled. If not, that is a reportable defect. Because if you had an issue and you needed to kill the power, how would you know which one to kill? You would have to kill them all.
Mm.
This I feel like I understand this a whole lot more than anything else because for some odd reason, I've dealt with breaker boxes a lot throughout my life, even to this point right now. It's kind of ghetto, but in the spa, we have to go hit the breaker when it shows where it's labeled with an AC. We have to go cut it on and off to regulate our AC because the AC stat thing isn't working. So we
Defect.
don't have that sensor, so we have to go cut it on and off at the breaker box. So it's cooking in my head the more you describe it.
Good.
I agree. I think the more you're like repeating it, honestly, I think you repeating it and actually drawing it. I even like drew the bus bar, right, and labeled it. And then as you were talking, I don't know, it just clicked. It was easier to process.
Thank you, Lord. Any other questions? I really want to fit in grounding and bonding, but I fear I might fry your brain. No pun intended. I feel like if I could get in grounding and bonding, we would connect another dot. But I may be out of time and capacity.
I'm with it personally, but it has to be a class effort. One flow.
Yeah, I'm good if you want to go ahead and.
We really need to give me a 1 if we can go grounding and bonding. We need maybe another 15 minutes to get in grounding and bonding. Give me a 1 in the chat if you want to get it in. Give me a 2 if you fried, died, and leg to the side. Oh, okay. We want to do it. Okay, let's go. All right. Grounding and bonding. So grounding is known as is also called earthing. It is essentially connecting electrical systems and or devices to the earth. You ever hear somebody say like stay grounded, walk outside barefoot? Well,
Yeah.
we are sending. Did somebody leave? We are sending our excess in a fault, or when something goes wrong, we send that current to the ground or to the earth. So that's why the thought is if you walk outside, because we are conductors, you can get some of that current, whatever the case may be. So that is what grounding means or refers to. It's a safety net for our electrical system. It provides a safe path for our current to flow into the ground if something goes wrong. Okay. Bonding is literally exactly what it sounds like. It's just connecting all of the metal parts in our electrical system, bonding them together, just connecting. That's it. It's not any sort of confusing technical term. It just means connecting. It's like holding hands. We want all our metal parts to be friends so that electricity doesn't jump between them without us knowing. So we bond them together. Okay, so let's start with grounding. Again, we are not just sticking a wire into the ground. We are building a complete path for our electricity or our current to safely return to its source if we have a fault or a problem. We ground to protect people and our equipment. If a fault happens, an example of a fault would be if a hot wire touches metal, the grounding provides a safe path for that electricity to flow back to the source. Okay? Grounding also helps keep our voltage stable throughout our electrical system. It prevents fires and also electrocution. Grounding happens in 2 main places. We have system grounding, where we are grounding or connecting our entire system to the ground. This happens at the main service panel. Then we have equipment grounding. This connects the metal parts of our appliances, our outlets, and our equipment to the grounding system at the panel. So think about this. Everything is again connected. So we gotta have grounding for our each piece of equipment. So each outlet, just think of a receptacle. Each receptacle has to be connected to the grounding system. How do we do that when the receptacle is in our upstairs bedroom and we got our panel downstairs in the basement? Bonding. So for grounding, we've got system and we've got equipment grounding. We use green or bare copper wires for our equipment grounding conductors. So when we see those green or bare copper wires terminating in our box on our grounding bus bar, we know that those are equipment grounding conductors, meaning conductors from each of our pieces of equipment or each of our loads that are now connecting back to that grounding bus bar in our main panel. So let's just say a metal part at one of our receptacles becomes energized. Our grounding wire, that's what you hear people say, our grounding wire or our EGC, equipment grounding conductor, will safely carry that current back to the main panel. So we accomplish grounding again by way of the grounding system. Three main parts of this system. We start with the grounding electrode. This is a conductive, again, a good conductor, a conductive object that we place in direct contact with the earth. If you've ever heard somebody say ground rod, they are referring to that is a grounding electrode. It creates the physical connection to the earth. Conductive, again, just means that something that allows electricity to pass through it very easily. So a ground rod is a metal rod, typically at least about 8 feet, that is driven into the ground. You can use a metal water pipe, concrete encased electrode, but just think grounding rod. So I've got my grounding rod that's driven into the earth. This is a grounding electrode. Now, again, everything has to be connected or bonded because I need a path. My current is flowing. It's constantly flowing. So I need a path that's uninterrupted. So I have my GEC or my grounding electrode conductor. This is the wire that connects the grounding electrode back to the main panel. So in our main panel, we will be able to see our grounding electrode conductor. It is typically a thicker copper wire. A number 6. We'll get into that next week, but it is a thicker copper wire. So again, it is carrying any of that excess electricity to the grounding electrode. And then I have what we just mentioned, my EGC. These are my green or bare copper wires that are inside, that are part of my branch circuits. They connect my appliances, my boxes, my devices to the ground. So if a fault occurs, then they can carry current back to the panel so that the breaker can trip. We're safe. So when you look at your grounding bus bar, which is again a metal strip in your electrical panel, all of your equipment grounding conductors, those are those wires that we're looking at. Our EGCs terminate on the grounding bus bar in our main panel. So again, Our electricity is going to enter the house, 2 energized conductors, 120 volts on each conductors. These are our hot wires. These are not supposed to be touching the grounding system. We don't want any current on the grounding system unless it's an emergency. There should be no current on the grounding system unless it's a problem. Okay? Our hot wires or our ungrounded conductors typically are black. So the current travels through the ungrounded conductors to the load, and then it wants to return to the source via the via the neutral. So we've got hot wire, appliance, neutral wire, back to panel, back to the transformer, because that's the source. But when we have a ground fault, meaning electricity leaks out of that path, out of the intended wiring, and it goes onto the metal frame of one of our appliances, a wet surface, a body, that is a ground fault. The electrical current has escaped from the normal wiring in the circuit and it flows onto something where it doesn't belong. This is where we need our grounding system. So what happens is the fault occurs and then our equipment, our current travels through our EGC, the equipment. So this is the load. Say this is a light bulb. We have a ground fault at the light bulb. The current would travel through the ground at the light bulb, the ground wire that's connected to the light bulb, which is a EGC. It will flow back to the panel. It will be terminating on that grounding bus bar. Remember, we talked about our bonding jumper, which is the metal strap that connects our grounding bus bar with our neutral bus bar. So now in the case of that fault, we've brought that fault current back to the panel where it can safely go back to the source and not electrocute you if you touch it, not cause a fire to another piece of metal or whatever the case may be. It has a safe, uninterrupted path back to the source or back to the ground. Our breaker would trip, killing the current or the flow of electricity, and we would be safe. Does that make sense? Question? All right. So bonding, again, bonding is just connecting metal components that are not supposed. These are the metal components that we don't want to carry current. So it's basically making sure, again, everything is linked so that there can be a quick and safe path for electricity to follow in case of a problem so that we don't have shocks and all that kind of stuff. So bonding is not sending the current to the earth. That's grounding. Bonding is making sure that any stray current, any stray electricity has, again, a safe, continuous path back. So we see bonding, again, in our main panel. In our sub panels, our neutrals and our grounds are not bonded. They are kept separate. Our appliances and our equipment, the metal frames are bonded with our EGCs. Let's look at it like this. So again, we got our power coming into the panel via our 2 hots. They're not shown here, but we know we got our 2 hots, our grounded, our neutral, 2 hots and a neutral that come in. The neutral connects to the neutral bar inside of the panel. This is our main return path for our electricity. The GEC, or the grounding electrode conductor, represented by this orange wire, This wire is connecting the neutral bus bar to the ground bus bar, and it is connected to the grounding electrode conductor outside. This is how we have a safe path back. Our GEC, grounding electrode conductor, which is a thicker copper wire, is connected to our neutral bar. It connects our neutral bar to the ground rod outside. See? GEC. We have a bonding jumper that connects the grounding bar and the neutral. This is only allowed in the main panel. Then we have our equipment grounding bar, our EGC, which is represented by our green or bare wire. It is bare copper wire. It is from the outlets, from your lights, and from your appliances. It is connecting back to that panel to the grounding bus bar. So we have an issue here at this load. Current is going to be flowing on the EGC, which is going to be connected to the grounding bus bar in our panel. Because of our main bonding jumper, the current can travel here, and our GEC, or our grounding electrode conductor, is going to carry that current to the ground, or to our ground rod that is outside. That is our path if there is a fault. Does that make sense?
Yes.
Any questions? So if everything is all good, we will have our electricity traveling to our load, power our light, return back via the neutral. That's what we want to have. If there's a fault or an issue, that is why we have our EGC that will carry the current that's done jumped out of line. It's supposed to be over here traveling back on the neutral. It's out of line. We need our EGC now to carry it back. It's going to terminate on that grounding bus bar. We have a metal bonding jumper that connects our grounding bus bar to our neutral bus bar. That's still a path. Our neutral bus bar has our GEC, our grounding electrode conductor, or our thicker copper wire. That wire is connected to the ground rod or the grounding electrode outside. So we are able to send our current to that excess current to the ground.
Question, are we supposed to know where that rod is outside? Like, would we know that?
Yes. You saying would you know it or should you know it?
I guess, should we know?
Yes, you want to be able to confirm that it's there, but keep in mind there are, when you read now, if you haven't read, go back and read. This should make the reading easier to understand. There's more than one type of grounding electrode. I'm just simply talking about the ground rod because that is common and it's easy to understand, but you can also have other types of grounding electrodes. So the answer to your question is yes, you do want to be able to identify and confirm that one is present. It may not be a ground rod.
Shouldn't you know if you have ground on your outlets? Because I know that I've seen houses with no grounding. I can tell by looking at the outlets
How can you tell?
because it doesn't have that. You know how when you plug in, it has that brown little circle underneath.
Uh-huh.
Well, some are missing, and that tells you that there's no grounding in that home.
That's good, Edith. That's real good, darling. You are absolutely correct. Those two-prong outlets those are typically older. We'll get into that next week when we talk about our receptacles, but here's the picture. This is how you know that receptacle does or should in fact have a ground wire. And when I was telling you to check out your receptacle, if you were to unscrew it, you would see the hot wire. It would be wrapped around here. We got lugs, essentially. It would be wrapped around one of these screws. The ground wire would be wrapped around the screw, and the neutral wire would also be wrapped around.
I don't know how that works, but I know that some investors don't want to spend. They don't want to hire an electrician to add ground, and what they do is
Bootleg.
I'm sorry.
They bootleg the ground.
Yeah, they don't. It's expensive, so they ask us to just do some GF. What are they called? The GFCI.
Yeah, FSCI.
Mm-hmm.
Yes, so they ask us to do those all over the houses, but I mean, we do whatever they ask us to. So I don't know how that works. So
I'm not going to get into that because I don't want to confuse you. We're going to talk about GFCIs and receptacles next week. But your point of those two-prong outlets are typically, again, they're older and they do not have a connection to the ground. And you're right. It is costly because you have to open up everything to be able to connect the ground, the EGC, back to the main panel. And you're right. Most investors would not want to do that. So they bootleg the ground. And again, I'll explain that next week. And that's why we use those electrical testers to tell us if we can indicate, if we can tell if there is a connection to ground. So you are understanding it correctly, Edith, from that perspective.
I hope so. I mean, I do, but the only thing I don't understand is still that circle you had us draw.
The circuit?
Yeah, the circuit. That area I just don't comprehend. I'll be needing to do some more reading on that.
The circuit, what we are representing is right here. Starting at the circuit breaker to your light and back. Remember when I said we wanted to go like this? That's the circle that I had you to draw. Because I wanted you to understand that concept first before we got into all of this. Power source, load, neutral.
Oh, okay. Thank you.
Mm-hmm. So, you see these larger, oh snap, I didn't mean to do that. These larger copper wires. These are your GECs. This is connected here. And it's also connected to your what?
Bus bar.
It's connected on the bus bar. Where's the other end connected?
Is it the ground?
The grounding electrode.
Yes, the grounding electrode. So in the case that I was using, when we were talking about a ground rod, the GEC. So it is on this right here. Do we have another one? Yeah, so this is a neutral grounding bus bar because we've got neutrals and we've got grounds. The thicker copper wire is our GEC that is connected to our grounding electrode or our grounding rod that's outside. So it could carry the current out there if necessary. So now when you're looking at your panel and you see your bus bars, as soon as you see these copper wires are thicker than any other wires that are than any of your branch circuits, I'll say, that are in the box. That automatically lets you know, oh, this is my grounding system in full effect. This is my GEC. I know you'll be able to follow it up and out. You won't be able to see, because you'll probably have stuff up there, but on the other end, you know that I'm connected to my grounding electrode, which is how I can safely send that current to the ground or to the earth. You see, here's one right here. It's coming here and it crosses over and goes out there. And now it's going again up and outside. We gonna I'm gonna show you this and then we'll get out of here. So the GEC is going back to the GE. So at your equipment, you got EGC, which goes back to your grounding bar. At the grounding bar, you have your GEC, your grounding electrode conductor, which goes to your GE, the grounding electrode or the ground bar. You see how that works? So we have a ground at our equipment. Remember we said that? Then we have our entire system that is then connected to the ground as well. I'm gonna stop while I'm ahead. Did that help?
Yeah, that was good.